So the motivation behind my work is one I think that we're all probably pretty familiar with, and that is that there is an increasing volume of space debris in space today that potentially poses hazards to the infrastructure that we rely on in our day-to-day lives. This happens just as a course of the way that space operations have been done in the past years. So there are things like stray rocket bodies that didn't really have a way to come back down from their orbit, or defunct satellites, or even fragments of satellites from collisions or ASAT testing that can, become very small, very fast-moving pieces of metal, silicon, what have you, that could potentially severely damage things like communication satellites or Earth observation weather satellites and so forth. One potential solution to this problem, as we start putting even more satellites into orbit and want to promote space sustainability, is autonomous space debris inspection and removal missions. The basic concept to this type of mission is that a servicer would rendezvous with a piece of space debris, identify it, characterize it however it needs to plan out the rest of its mission, and then make a docking or grappling maneuver to intercept that target, so to speak, and deorbit it safely and remove it from the orbital environment where it won't pose a hazard anymore. So I mentioned, characterizing, observing, inspection as part of that process. That's sort of the part that I'm zooming in on. So one of the needs that this servicer has is to be able to characterize both the shape and the pose of the target. And this is a target that is potentially unknown ahead of time and potentially undriven, uncooperative. It's not going to be maneuvering in a way that is helpful to that servicer. So this guy is the problem statement that I've chosen to investigate for the time being. I'm seeking to develop an estimation pipeline to rapidly and reliably estimate the pose and shape of an uncooperative, unknown spacecraft using images from a single onboard camera. This would enable us to carry out this kind of mission with missions and sensors that are relatively inexpensive, which again enables larger scaling of this type of a mission. As I'm sure we've been hearing from some other presentations that people have given in here, there's plenty of existing work that sort of seeks to address similar issues. Particularly, there are a few different classes of techniques for characterizing the shape and pose of some unknown object, particularly a space object. We have certain techniques that are somewhat tried and true. I've separated these into some broad categories. So the first one I would say is a category where we're learning a model based on many observations of the target over time. One of the most basic of these is what we call structure from motion. So essentially you are sampling features, you're detecting features from your target, and fitting an estimate of where those features are in space or where they are on your target, as well as your trajectory to those observations. And you use bundle adjustment over time to refine those estimates in groups. We can build upon that technique using simultaneous navigation and characterization, which is sort of a big umbrella term that can encompass a lot of specific implementations of these techniques. The big picture here is that you can estimate the relative pose and many different target parameters. So that could be the features as a point cloud, or it could also be things like if your target is an asteroid, you might estimate what its gravitational field looks like, or other environmental characteristics that you might be able to detect. This is often still initialized with structure from motion, so I would say those techniques are not necessarily completely separate, but they the benefit of SNAC is that you can sort of iteratively refine that, sometimes using something like Kalman filtering. And then one other technique that's kind of emerged more recently, I would still kind of group in this large category of learning a model from many observations. That these techniques would be what I'm calling here view reconstruction techniques. So there are certain techniques that are really designed and optimized to construct very high fidelity images of views of a target or views of an environment that haven't specifically been sampled yet, but you're still able to build up a very high fidelity model through other views of that same target. So one of these is NERF, which trains a network to represent these radiance fields that you can sample from different angles to produce those views from those other views, those images from those other views. Another one of these is Gaussian splatting, which is sort of representing the volume in space with these Gaussians of different weights and colors. But I want to emphasize that even though these are kind of new and exciting right now, they do still have some of the same limitations as the other techniques in that they still require you, the techniques that have been used on Earth typically expect you to know the viewer's position as you construct these models. If you want to construct it in space with an unknown model and maybe an unknown relative pose, you're still probably going to rely on one of these feature tracking techniques from above to establish your estimates of what those poses are as you construct the model. The other big category that I would categorize these techniques into is offline training of machine learning models. You've heard a lot about this recently from Jeff, so I'll keep it a little bit brief, but the general principle here is that if you have a general idea of what your target is going to look like, you know it's a spacecraft, you know it's going to have features that we see a lot in spacecraft, like maybe solar panels, maybe antennas, probably boxy bus structure, for instance. You can train that model on images of spacecraft that have those features ahead of time, with the expectation that it can then infer what it is seeing when it looks at the spacecraft in space very quickly, however long it takes to evaluate your network from one image. So this would enable you to produce an estimate of the shape and pose of your spacecraft from just one image. So we saw Jeff's work on this, where he is reconstructing the shape of the spacecraft as an assembly of shape primitives called superquadrics. I'll be revisiting this. There's some related techniques that I think I need to do a little bit of reading about, but object SLAM is an example of a technique that is generalizing shapes into certain shape primitives, also producing estimates of the pose, and then has the option to tie together some semantic information about multiple objects in the scene. So that's sort of I'd say sort of related to the work that we've seen from Jeff. There are other techniques that use sort of higher resolution shape representation. So you can, for instance, use meshes with nodes and edges that represent the shape of the spacecraft, or you can use volumetric voxel-based representations. These are just a couple examples here. One disadvantage of these types of techniques is that it can be very data heavy. You imagine the number of voxels you need to represent fine details in a spacecraft. It can get a little bit unwieldy. I've shown a few figures here on the right. Apologies that the one on the bottom is a little tricky to read. I'm showing a bit of a zoomed in look at the first example that I mentioned on this slide, which is the work that Jeff published earlier this year at SciTech. So the general principle of this model is, like I mentioned before, you feed it an input image, just one image, and then it evaluates and produces an estimate of the shape in the form of this assembly of shape primitives, as well as a pose estimate, and that's a rotation and a translation estimate. It has its advantages and disadvantages. So as we saw with some initial testing from this, it handles the spacecraft that it has seen models of during training very well. So you can see those are the blue models in these graphs. The top is a measure of the shape quality, the estimate of the shape's quality, and then the bottom is an estimate of the rotation quality. So you can see the testing set is in red, and the validation set, which are spacecraft that it has seen before, is in blue. So in the case of the spacecraft it has seen before, it really handles those decently well in terms of the shape estimate, but it struggles a lot more with spacecraft models that it has never seen during test training. So there's a bit of improvement to be done there. More concerningly, perhaps, we see pretty high errors across the board in rotation error. So this is another area that we would like to improve if we're going to make this model a bit more operationalizable. So we'll discuss that a little bit more in future slides. So the advantage of this approach here, however, is that it's pretty lightweight. So it's representing these shape primitives with a fairly short list of primitives. Representing the shape primitives with a fairly short list of parameters. So it takes 16 parameters with this implementation to represent one primitive. The prior work used 8 primitives to represent the spacecraft shape. That is not really an unreasonable number of parameters to handle. The downside that I mentioned before, it's prone to some high errors in rotation and reconstruction. I have some examples here on the upper right. So the top row is a picture of the Hubble Space Telescope, which our model was trained on during its training. It was one of the spacecraft it saw during training, but it's not an image that it saw during training. And you can see, even though it's a new image, it still produces a quite good looking model, right? The second image was a spacecraft that it did not see at all during its training. And you can see that it's struggling a lot more to reconstruct this. So the blocks don't really resemble the shape at hand anymore. Clearly a bit of room for improvement there. So my proposed approach here is to incorporate the elements that we saw from both of those large categories of these shape and pose estimation methods. So incorporate the rapid, pre-trained approach that Jeff has taken in his superquadrics work with the filtering and iterative refinement approach that we saw in some of the SNAC and SLAM-based techniques. So what this would look like is incorporating this neural network into a filtering scheme where the outputs of the network form a measurement. Maybe I'll call it a pseudo-measurement, so I don't have to do air quotes all the time. But it forms a measurement or pseudo-measurement that we're going to feed into our filter. And then that filter can be informed by knowledge of the relative dynamics of the spacecraft in order to produce a more refined and more informed estimate. And that might be able to coast through periods where the image quality is poor, as well as just provide continuous iterative refinement on things like the spacecraft shape, which may be noisy no matter how good your images are. Another benefit to this that we saw in some other work from this lab is this kind of implementation may eventually be able to provide online retraining or online supervised training of the model. So this would look like if you have an output to your network that is poor, or perhaps it's just an input of the image, that input in the network that is out of the distribution we trained with, we could take the outputs from our filter, add pseudo labels to that image, and calculate the loss and retrain the network based on the loss there. Another direction that I'm going to be looking into is how else can I improve the network itself without even looking at the filter. So it's fairly early work. It was only published this year. As great as it is, there's plenty of other directions to be explored that just haven't had a chance to be explored yet. So I'll actually start out with those. I've borrowed a figure here from Jeff's presentation. This is essentially an overview of what the training process looks like. So I'll call out here really quick. There's four different loss functions that are used to train the network. So one of these is a pose loss, which is sort of a combination of the rotation and translation error. And then there's these three loss functions that are all related to the shape reconstruction. So this one over here is occupancy loss. So it's sampling points inside the shape representation and checking if they match what the actual ground truth shape is. This is chamfer loss, which is sampling points on the surface of the spacecraft, estimate, ground truth, comparing them. And then we have a reprojection loss, which is projecting the spacecraft into the image plane and looking at the silhouette of it and checking which pixels overlap and which ones don't. There have been some discussions that I think suggestions people in here have given, as well as discussions that Jeff and I have had, and we've come across a few different ways that these can be adapted a little bit. So one of these is, I've mentioned, there's these different training loss functions that we're using. Right now, they're all just kind of weighted the same way, but it's very possible that the optimal way to train this might be to put more emphasis on one of these loss functions than another one. So that's sort of a low-hanging fruit that I'm planning to explore here, is trying out a few different combinations of relative weights for these different loss functions to see if perhaps weighting something like the pose loss a little bit higher might incentivize better matches in the rotation estimates, for instance. Another point that is, well, there's two of these that are related a lot to the pose error, specifically the rotation error. That's the one that I mentioned before is a particularly challenging one with this network. Spoiling a little bit of the information I'll give you on a later slide, a lot of these issues happen when we have spacecraft that have two really long solar panels so that it looks rather symmetrical. If you have one solar panel, it's pretty easy to tell how you're oriented, but if you have two, you can imagine the spacecraft could be flipped around like this or like this, and it might have a really similar looking silhouette. So we're looking for ways to incentivize better pose estimates despite those challenging inputs. So a few different directions that could be helpful here is there potentially could be a way to incentivize asymmetry by adapting the number of primitives that we use in the reconstruction. Right now, 8 is what was performing best in the prior work, but perhaps in these highly symmetrical spacecraft, we can incentivize fitting some other smaller feature on the spacecraft, for instance, to make that pose estimate a little bit easier. Another direction that I'm looking into is what if we incorporate the pose into these other loss functions that don't directly measure the performance of your pose estimate. So right now these are decoupled from the pose estimate. So essentially we're using ground truth pose in the reconstruction loss, and we're not using any pose estimates for occupancy and chamfer. But potentially, maybe there's some benefit to incorporating in the loss, the pose that we've estimated earlier. So In parallel with these improvements to the network itself, the bulk of my work is going to be looking more into how to incorporate this network into a filtering scheme. The initial direction that I'm going here is in incorporating it into an unscented Kalman filter. These are a good balance for space missions in that they can handle nonlinear measurement models and nonlinear dynamics. However, they're fairly lightweight. They don't have the computational complexity of something like a particle filter. So as I mentioned before, the general principle here is we would treat the outputs of the neural network as sort of a coarse measurement and feed that into the filter. The filter is going to be propagating the dynamics with the STM. It's going to use a multiplicative approach to filtering the quaternion, which is the preferred method for those types of rotation estimates. The state vector is going to look something like what I have here. So essentially we'll have the relative orbital elements, modified Rodriguez parameters to represent the orientation, angular velocities, and then shape parameters for however many shape primitives are in the assembly. A cool thing about those shape primitives is they're not really affected by the dynamics. So we're able to make, well, at least initially we'll make an assumption that the spacecraft shape is static over time. It's not wiggling around its panels or antennas or anything like that. So we don't need to propagate dynamics for the shape parameters, but we can still rely on the UKF just because we already are implementing it for pose. We can also feed those parameters in there and let the multiple measurements be used to refine that estimate. So I've done a bit of exploration into what the error distributions look like in order to give informed error covariances to the filter. So I did a lot of my investigation has been focusing on the rotation errors because, as I mentioned before, these are sort of our most concerning errors that come out of this network. An interesting trend has kind of emerged from that. So you can see here on the left, I looked at the rotation errors just for satellites that have a single solar panel. Like I mentioned before, those are sort of asymmetrical spacecraft that in theory should be fairly easy for our network to estimate the rotation of. And then I also looked at the rotation errors for these spacecraft that have two solar panels. Almost all of these have these really long panels and relatively small bodies that could be seen as being fairly symmetrical. Maybe not exactly symmetrical, but pretty close to symmetrical. So you can see here, the blue outlines, the blue shapes are representing the errors in the validation set. So these are spacecraft whose models were seen during training, and then the red ones are from the test set whose models were never seen during training. I think there's two main trends that emerge here. Number one, across the board, it struggles a lot with the test set. The test set has these very high errors no matter what. Number two, we see a bimodal distribution emerging on the spacecraft that have the two extended solar panels. This is sort of the worst case scenario for our filter if we assume that the network is going to continue having this output. Maybe I can improve it so that it won't output this sort of a trend, but for now I'm going to assume this is the kind of error distribution I'm dealing with and try to figure out how to filter that. So the investigation that I'm currently working on is feeding in a surrogate distribution that represents this distribution into a Kalman filter, UKF, to understand how well it can handle this, given that the UKF assumes that you have Gaussian measurement errors. This would also help me, presuming it can handle it, this would help me tune what my estimates of those covariances for all of the measurement errors are, not just for rotation, but also for translation and the shape parameters in order to get good performance from my filter. The eventual goal here, of course, is to do sort of an end-to-end test of this entire estimation pipeline, connecting both the network and the filter. But to do that, I need some kind of a sequential data set with spacecraft that are the same type as what was seen during training of this network. Unfortunately, the SHIRT data set is a different style of spacecraft than we trained the network with, so it's not really ideal. We're going to need a new data set. So this is something that I'm hoping to start working on soon. And like I said, this will let us do sort of a whole sequence of images fed into the network, then fed into the filter, and investigate the quality of those outputs. In the more distant future, there's some other interesting directions that this could go. So number one, we have some more sophisticated UKF implementations that this lab has produced that would be great to incorporate into this. So particularly adaptive state noise compensation was very beneficial on the SPN work, so it probably would be beneficial here. Additionally, we've seen some success from online supervised training, again in SPN. Potentially there's some benefits here as well. So essentially what this would do, when we're training a machine learning model, usually we want to avoid overfitting, right? We don't want our model to be too specific to any one input that it might see. But once you deploy this kind of a estimation pipeline in space, and you're doing an encounter with a particular target, at that point, it may actually be beneficial to overfit that model in that we want it to really be good at estimating the shape and the pose of whatever spacecraft is looking at that time. So if you could retrain it to bias itself a little bit towards that type of spacecraft, that might give it some improved outputs. So that's the concept of this online supervised training, where we could sometimes, whether triggered by maybe an input image being an outlier compared to the training set, or maybe just at random intervals if we're not being as picky about it, we would take the outputs from the filter, apply pseudo labels to that image that we were just looking at, and feed the loss back into the network to retrain it. That way you're sort of treating your filter as an expert that has good knowledge of what the true state of the other spacecraft is. So this is the direction I'm going. Happy to hear if anyone else has any ideas about where I can go or any questions for me. As I'm sure you can tell, things are in an exploratory stage, so there's a lot of different ways that this can go in the future.